Welcome all. In this lecture, we are going to learn about boundary condition at media interface. So let's discuss about boundary conditions first. So according to the definition of boundary condition, the conditions that the field must satisfy at the interface separating the two mediums is known as boundary condition. So let's suppose here is the medium 1 and here is the medium 2, and this is nothing but interface. Now at the interface some conditions are applicable and should be satisfied, and these conditions at the interface are nothing but boundary conditions. Moving on to the next definition, that is, the boundary conditions are helpful in determining the field on one side of the boundary if the field on another side is known. Let's suppose that we know the field at the interface of medium 1, but we didn't know the field at this medium. So to know the field on the other side, that is medium 2, we should require the boundary conditions. So the boundary conditions should be satisfied at the interface of the two medium that are separated by this interface. Now let us discuss more about the requirement of boundary conditions. So if we have to calculate the electric field in the region consisting of two different mediums, then we must require the boundary conditions on the interface of two medium also. So here is requirement of boundary condition. So let me write it. So here is the theory that we written, and here are the two medium, and if we want to calculate the electric field in the region consisting of these two medium, then we must require the boundary condition at the interface of these two medium. So to calculate the electric field also we have to require the boundary condition at its media interface. So this is all about the introduction and definition and requirements of boundary condition at its media interface. Now the boundary conditions is also helpful in understanding the continuity and discontinuity of medium when the electric field enters from one medium to another medium. So let us understand the boundary conditions for electric field. So here is the boundary conditions for electric field. To understand this concept, let us consider a interface or the surface. This is the interface between medium 1 and medium 2. So when the electric field enters into this medium, then it shows either continuity or discontinuity behavior. So the boundary conditions is helpful in understanding the continuity and discontinuity of medium when the electric field enters into it, and the boundary conditions are applicable only at the interface, because these are only those conditions that should be satisfied at the interface only. Now for the electric field, the boundary conditions, we have to find out the tangential and normal component of electric field. So let us first discuss about the tangential component of electric field. So to discuss the tangential component of electric field, let us consider a surface or the interface. So above the surface there is a dielectric constant. So the dielectric constant above the surface is represented by epsilon r1, and the dielectric constant below the surface of the medium is represented as epsilon r2. Now here is the tangential component for the medium 1 of the electric field, that is represented as ET1, and here is the electric field, tangential electric field component, that is represented by ET2 because it is of second medium. Now let us consider a closed loop in the clockwise direction. following the 4 points, that is A, B, C and D. So here is A, B, C and D, and it is making a closed loop in the clockwise direction. So here is the clockwise direction. Now technically the distance here is represented as del x, and the distance between A and D is del y. So this is the introductory part of the whole structure, in which there are the two medium, that is medium 1 of the upper surface and the medium 2 that is below the surface, and this surface is nothing but interface between these two medium, having the tangential component, that is ET1 for the upper surface and ET2 for the below surface. As per the Maxwell second equation, we know that line integral of electric field is equals to 0. Now if we discuss the line integral of electric field over the surface separately, then we can write it as E dot dl for A to B plus line integral of E dot dl for B to C plus E dot dl for C to D plus E dot dl from D to A equals to 0. We are only following the clockwise path, that's why we are taking the integral limits from A to B, B to C, C to D and D to A. Now we can write in terms of electric field component, that is tangential, that is ET1 and ET2, as this E dot dl over the integral A to B can be written as ET1 dot del x, because the direction of the A to B is like this, and here also the direction is like this, that's why having the same direction, here is a positive term. Now here is B to C limit, so here is the B to C, but in this direction there is no component of electric field, that's why it becomes 0 only. Now here is the D to C, so here is D to C. Now our integral is in the direction opposite to the direction of electric field component, so we can write it as negative of ET2 into the distance is del x plus here is the integration from D to A, so in the direction from D to A there is no electric field component, that's why we can simply write 0 here and equals to 0 only. Now we can also write it as, by taking the del x common, we can write ET1 minus ET2 into del x is equals to 0, or this can also be written as ET1 is equals to ET2 or ET1 minus ET2 is equals to 0. Since ET1 minus ET2 is equals to 0, that's why we can say that the electric field is continuous for tangential component. The electric field is continuous for tangential component. So this is all about the tangential component of electric field. So from the evaluation we know that the electric field is continuous for tangential component. Now let us discuss about the normal component of electric field. But before discussing about the normal component, let us write this result, that is the electric field in terms of electric flux density. So the electric field component or the tangential component of electric field can be written in terms of electric flux density by the formula. We know that the electric flux density D is equals to epsilon 0 epsilon r into E. So from this formula we can also write the electric field as E equals to the electric flux density divided by epsilon 0 epsilon r. If we write the tangential component of electric field in this form, then it will become dt1 over epsilon 0 epsilon r1 is equals to dt2 over epsilon 0 epsilon r2. Now from the LHS and the RHS, this epsilon 0 will get cancelled with this epsilon 0, and the remaining term that we get is equals to dt1 over epsilon r1 equals to dt2 over epsilon r2. Now if we take this dt2 in the denominator and this epsilon r1 in the numerator, we get dt1 over dt2 is equals to epsilon r1 over epsilon r2. So this is the expression for the tangential component of the electric field in terms of electric flux density. Now let us have a look at the normal component of electric field. So for evaluating the normal component of electric field, let us discuss about the surface. So here is a surface and this is the direction, that is the electric flux density above the surface, that is represented by dN1, and here is the direction of the electric flux density below the surface, that is in the downward direction and is represented by dN2. Now the dielectric constant above the surface is epsilon r1 and the dielectric constant below the surface is epsilon r2. Now let us consider a Gaussian surface. So here is the Gaussian surface. Please note that this Gaussian surface is very small, but for the representation I am drawing this as a large. So here is the Gaussian surface. This height is nothing but del z. This width is represented by del x and the length is represented as del y. And we also noted that this del z, that is the height, is very small or tends to 0 only. Now we will calculate the electric flux density with respect to this Gaussian surface. So electric flux density with respect to this Gaussian surface is given as, according to the Maxwell's first equation that we studied, that is surface integral of ds is always equals to charge enclosed by that surface. So if we consider this Gaussian surface, then here are the 6 faces of this surface. This is the top surface, and in the bottom here is the bottom surface. This is the front surface, and in the backward direction there is a backward surface or the back surface, and here is the right surface and here is the left surface. So the total number of surfaces are equals to 6. And if we break this integral over a closed surface into the integral of these 6 surfaces, then it, for the top surface we write d dot ds of top plus d dot ds for bottom surface plus d dot ds for front surface plus d dot ds for back surface plus d dot ds for right surface, and finally d dot ds for left surface equals to charge enclosed by that surface. Now by the help of this figure we can know that the direction for the electric flux density is in the top direction. So for the top surface the direction is also pointing in the upward direction, that's why it will be positive, and for the bottom direction we can take it as negative component. So for the top we take it as dn1 into, for the top surface here is the two parameter, that is length and breadth, that is multiplication of del x and del y. So del x into del y. For the bottom surface the component is in the downward direction, negative. So here is minus sign and dn2, and for the bottom surface also there are two parameters, that is del x and del y. So del x and del y. Now for the front surface there are two parameters, that is length and also height, and since we assume that del z is 0, that's why this whole component will become 0. For the back surface here is also two components, that is del z and del y, and del z is 0, that's why this also 0. Similarly for the right surface there is del z and del x. Since del z is 0, therefore this 0 and the left component is also become 0, equals to the charge enclosed by that surface. Now on taking this del x and del y as a common, we get dn1 minus dn2 del x del y is equals to charge enclosed by that surface. So this can also be represented as dn1 minus dn2 equals to q over del x del y. Now this del x and del y is representing the area only, that's why we can also write dn1 minus dn2 is equals to rho. This rho represents the surface charge density. And by analyzing this equation we can say that the electric field is discontinuous for the surface charge density. Electric field is discontinuous for normal component. So this is all about the normal component of electric field, and in this lecture we discussed all about the boundary conditions at media interface. If you like my videos, then do subscribe my channel and press the bell icon for further notification. Thank you. Welcome all. In this lecture we are going to learn about application of transmission line. So the most application